imagine a museum, but not just any museum.
Yeah.
A museum that could hold everything.
Everything. Yeah.
Like, not just, dinosaur bones
Right.
or ancient artifacts.
Yeah.
But like every mathematical concept, like ever dreamt up.
Oh, wow.
Even the ones, so big that they like warp the fabric of infinity itself.
Yeah.
Could such a museum, like a blueprint of the infinite, could it even actually exist?
I mean, that's a mind-boggling idea, right? And that's kind of what's at the heart of this idea of ultimate L.
Ultimate L.
Yeah. It's a concept that is really sending ripples through the world of set theory. It's a really big deal.
Yeah. You sent over some fascinating excerpts on this, and honestly, I'm still trying to like wrap my head around it all. We're talking about mapping infinity, right?
Yeah.
But where do we even begin with something that vast?
Right. So I think it all starts with kind of understanding the sheer scale of what mathematicians are dealing with here. We have this idea of V, the set universe. It's basically the ultimate container for everything mathematical. So every number, every equation, every possible set, all nestled within this enormous V.
Okay. So V is everything. Like if math were a video game, V would be the entire game world, right?
Yes.
Every level, every character, every secret Easter egg.
You got it.
Like it's all in there somewhere.
Yeah, but here's the thing. V is so vast, so overwhelmingly complex, that it's almost impossible to study directly.
Right.
It's like trying to explore, I don't know, a continent-sized jungle with no map, no compass, just dense, tangled vegetation as far as the eye can see.
So how do mathematicians even begin to make sense of something that massive? Do they just like throw their hands up in the air and say, well, it's infinite, guess we'll never understand it?
I mean, they could, but that wouldn't be much fun, would it?
No, not at all.
So instead, what they've come up with is this really ingenious idea called inner models. And think of these as carefully curated exhibits within our vast mathematical museum.
Oh, so instead of trying to like grasp the entire jungle at once,
Yeah.
we're focusing on specific clearings.
Right, exactly.
Maybe a grove of particularly interesting trees or like a hidden waterfall.
Yeah.
And we can study those smaller areas in detail.
Yeah.
And maybe, just maybe, that'll give us clues about the larger jungle as a whole.
Exactly, and I love that analogy. And one of the most famous exhibits or inner models is Gödel's constructible universe, which is denoted as L. And it's this beautifully ordered section of V where everything has its designated spot, its own logical address within the system.
So L is like the meticulously organized section of our museum, where all the artifacts are perfectly labeled, the displays are spotless, and you can find exactly what you're looking for in like an instant.
Yeah.
But
Yeah.
there's a catch.
Yeah, there's always a catch.
This is where the ultimate L mystery comes in. Yeah, you're catching on quickly. So the problem is L, for all of its elegance, and order can't quite contain everything within V.
Oh.
There are these colossal objects lurking out there.
Uh-oh.
Entities so vast that they kind of strain the very fabric of this mathematical universe.
Yeah.
And we call these large cardinals.
Okay, large cardinals.
Yeah,
They sound intimidating.
they are.
Are we talking about numbers so big they make like a Googleplex look like a grain of sand?
It's more than just their size, although their size is definitely mind-boggling. Large cardinals are less like individual numbers and more like, I don't know, fundamental forces, you know, like shaping the very structure of V. Trying to squeeze them into a neat, well-behaved model like L is like trying to fit a supernova into a teacup.
Right. Yeah, it's not going to...
It just doesn't work.
It's not going to work.
Yeah.
So we have this beautifully organized museum exhibit L, but then we discover these colossal cosmic entities, these large cardinals that are just too wild,
Yeah.
too powerful
Way too powerful.
to be contained within its walls. Right.
What do we do? Do we just like give up on having a complete museum of mathematics?
Well, that's where the quest for ultimate L begins.
Yeah.
Imagine trying to design a museum that could not only house, the neatly categorized exhibits of L, but also accommodate these immense reality-bending large cardinals.
Right.
That's the challenge that mathematicians have set for themselves.
Yeah.
And it's a challenge that has the potential to, I think, revolutionize our understanding of infinity itself.
Okay. I'm starting to see why this is such a big deal. But how do you even begin to build something that can contain the uncontainable? What kind of mathematical blueprint could possibly handle those colossal large cardinals and maintain the elegant order of L? That sounds like trying to mix oil and water or fire and ice.
You're right. It's a monumental task, no doubt. But that's what makes it so fascinating, right? It requires pushing the boundaries of set theory, developing entirely new techniques, and, a whole lot of creative problem solving. And who knows, maybe in the process of trying to build ultimate L, we'll discover something even more profound about the nature of mathematics itself.
This is already making my head spin.
It's a lot to take in.
But I am so hooked. We've laid the groundwork,
Yeah.
introduced the players,
Mm.
the vast V, the ordered L, and the unruly large
The
cardinals.
gang's all here.
But how do these pieces fit together? What are the tools, the techniques that mathematicians are using to try and build this ultimate L?
Yeah, the how.
We'll delve into those fascinating details right after. Before we jumped into the how of building ultimate L,
Right.
we were grappling with the sheer scale of V and the challenges posed by those unruly large cardinals. It's like trying to create a map of like a constantly shifting landscape.
Yeah.
Where mountains rise and fall, rivers change course, and new islands just appear out of nowhere.
That's a great way to put it, yeah.
Right. And our trusty L, well, beautifully organized,
Mm.
it's just not equipped to handle that level of like dynamism. It's like trying to use a street map of Manhattan to navigate the Amazon rainforest.
Yeah.
The rules of the game are just fundamentally different.
Totally.
You mentioned that mathematicians are like developing new tools,
Right.
new techniques to tackle this challenge. What are we talking about here? Give me the insider scoop.
Okay. So one of the most powerful tools in their arsenal is a technique called forcing.
Forcing.
Yeah, forcing. Now, forcing is a bit tricky to explain, but think of it like this.
Okay.
Imagine you have a perfectly clear picture of the night sky. You can see all the stars, the constellations, everything laid out in its proper place, but then you put on a special pair of glasses.
Okay.
These are your forcing glasses.
Forcing glasses. I like it.
And suddenly, new stars appear. Constellations rearrange themselves. And the entire cosmic landscape just shifts before your eyes.
Okay, that's a pretty cool visual.
Right.
But I'm guessing it's not just about like making the universe look prettier, right?
It's a little more than that, yeah.
What's the like point of this mathematical rearranging?
So the brilliance of forcing is that it allows mathematicians to explore alternative possibilities, to see what happens when you tweak certain fundamental assumptions
Oh, interesting.
about the mathematical universe. It's like running simulations, testing different scenarios to see how the system responds.
So it's not about changing the universe itself.
Right.
More like tweaking the parameter.
Exactly.
Adjusting the settings.
Yeah.
To see what new patterns or structures emerge.
Right.
Kind of like those what-if scenarios
Exact.
in
right.
like history books.
Yeah.
What if the Romans had never fallen? What if electricity had been discovered a century earlier?
Exactly.
That kind of thing.
Yeah, so forcing allows mathematicians to ask those what-if questions about the very foundations of set theory.
Fascinating.
And by exploring these alternative realities, they gain a deeper understanding of the underlying rules governing the system as a whole.
That makes sense.
Yeah.
But I'm still a bit fuzzy on how this connects back to Ultimate L.
Right.
We're trying to build this all-encompassing museum.
Yeah.
But how does like messing around with forcing glasses help us achieve that?
Yeah.
Doesn't just make things more complicated.
Potentially, yeah. And that's where the real challenge lies. While forcing is incredibly powerful, it can also be a bit of a double-edged sword. By creating these alternative realities, it can sometimes blur the lines between what's true and what's merely a product of our forcing manipulations. It's like trying to build a house on shifting sands. You need a solid foundation, a reference point to anchor your construction.
And that's where like inner models come back into play, right? They're like the bedrock,
Right.
the stable ground beneath our feet, even when the forcing winds are swirling all around us.
You got it. Inner models, especially Ultimate L, if we can ever build it, provide that crucial stability. They act as a guide, a compass, to help us navigate the potentially disorienting effects of forcing.
So if forcing is like the special effects team
Okay, yeah.
in a movie,
Yeah.
creating, dazzling visuals
Yeah.
and mind-bending scenarios,
Yeah.
then inner models are the script writers,
I like it.
ensuring that the story stays consistent,
Right.
that the characters and the plot don't get lost in the spectacle.
That's another brilliant analogy. An Ultimate L, if it exists, would be the ultimate script, the definitive guide to how the mathematical universe operates, even under the most extreme forcing conditions.
Okay. I'm starting to get a feel for the complexity of this task.
That's a lot.
We have these powerful tools like forcing,
Right.
but we also need the stability,
Yeah,
and the clarity provided by inner models.
exactly.
That's like a delicate balancing act,
Yeah. Yeah.
pushing the boundaries of what's possible
Yeah.
while ensuring that the entire structure
Yeah.
remains like logically sound.
Exactly. And that's what makes the search for ultimate L so captivating. It's a testament to the ingenuity and creativity of mathematicians, their willingness to grapple with the most profound questions
Hmm.
about the nature of infinity and the very foundations of mathematics itself. But it's not just an abstract pursuit, a game played out, in the ivory towers of academia. Understanding ultimate L could have profound implications for our understanding of the universe as a whole.
Okay, hold on.
Yeah.
Now you're really piquing my curiosity.
Okay.
How does this abstract, mind-bending math
Yeah.
connect to, like, the real world, the
Okay.
universe we see around us? I'm all ears. So we left off talking about how this quest for ultimate L,
Right.
this, like, seemingly abstract mathematical pursuit,
Yeah.
could actually have implications for understanding the, like, real universe, the
Mhm.
one with stars and planets and well, us.
Right.
How do we get from these mind-boggling sets and cardinals
Mhm.
to something we can, like, actually observe and measure?
I think it all kind of boils down to the nature of truth
Right.
and how we go about finding it. For centuries, physics and mathematics have been like intertwined,
Yeah.
each informing and enriching the other. Think about Einstein's theory of relativity. I mean, it revolutionized our understanding of gravity, but at its core, it's a mathematical framework, right? It's a set of equations describing the curvature of space-time.
Okay, yeah. I'm following so far.
Good.
Math provides the language, the tools for describing the universe.
Yeah.
But where does ultimate L fit into all this? Is it like the ultimate physics equation just waiting to be discovered?
Well, it might not be an equation in the traditional sense, but it could provide, I think, a deeper understanding of the underlying structure of reality.
Okay.
You see, one of the core questions in physics is whether the universe is fundamentally deterministic
Okay.
or probabilistic.
Okay.
In other words,
Yeah.
is everything predetermined, like a clockwork mechanism?
Right. Or is there an element of randomness, of chance,
Mm-hmm.
like baked into the fabric of existence?
Okay, so like big questions here. Determinism versus randomness.
In questions, yeah.
But how does set theory, how does ultimate L help us answer that?
Well, ultimate L, if it exists, would suggest a profound level of order
Yeah.
and structure
Yeah.
inherent in the mathematical universe.
Okay.
Now, whether that mathematical order directly translates to physical reality is a question for, philosophers and physicists to debate. But it certainly provides a fascinating perspective.
So it's like if ultimate L can be built, if we can like demonstrate that even the most complex infinite aspects of math can be contained within a logical, consistent framework,
Yeah.
then maybe, just maybe, that hints at a similar order underlying the physical universe as well.
Exactly. It's like finding a hidden code, right? A blueprint that governs not just the behavior of numbers and sets.
Right. But also, the fundamental forces shaping the cosmos. Of course, this is all highly speculative, but that's the beauty of exploring these cutting edge ideas, right? They push us to think beyond the familiar, to question our assumptions about the nature of reality itself.
Yeah. My brain is definitely doing backflips right now, but in a good way.
Good.
But let's step back for a moment and talk about the process itself.
Okay.
We've talked about the what and the why of Ultimate L.
Yeah.
What about the how?
Mm-hmm.
What does the actual research look like? Are we talking about like lone geniuses, scribbling equations on chalkboards,
Yeah.
or is this more of a collaborative effort?
It's definitely a team effort. It's a global community of mathematicians working together, building on each other's ideas, pushing the boundaries of set theory. They're developing new proof techniques,
Right.
refining existing models, and constantly searching for that breakthrough that could lead to ultimate L.
So it's like a massive construction project.
Uh-huh.
But instead of bricks and mortar,
Yeah.
they're using like logic and proofs as their building blocks.
Mm.
And every new theorem, every new model is like adding another piece to the puzzle, getting us closer to the complete picture.
I love that. Yeah, that's a great way to visualize it. And just like any complex construction project, there are bound to be, setbacks, challenges, and moments where it seems like the goal is just out of reach. But I think the progress made so far is truly remarkable. We're seeing models that capture more and more of the properties that Ultimate L is predicted to have. So there's definitely a sense of optimism in the field.
So even if we haven't reached the summit yet, we're definitely making our way up the mountain.
Right.
And the view from each new vantage point is pretty breathtaking.
Yeah, I would agree with that.
Well, I think it's safe to say our minds have been thoroughly expanded today.
I think so too.
This deep dive into Ultimate L has taken us on a whirlwind tour through the most, mind-boggling corners of set theory,
It's a wild
from
ride.
the vast V to the elusive Ultimate L itself.
The whole shebang.
We've talked about forcing, inner models, the nature of infinity, and even touch on the philosophical implications of this research.
Yeah, it's been a lot. It's been great, though. It's been a true pleasure sharing this journey with you. And to our listeners, we hope this exploration has sparked your curiosity about the incredible world of mathematics and the profound questions it seeks to answer. Remember, even if Ultimate L remains, a distant goal, the quest itself is full of wonder, discovery, and the thrill of pushing the boundaries of human understanding. So keep exploring, keep questioning, and never stop diving deep into the mysteries of the universe.